Test the day, everybody. So today I'm going to start one topic that is what we call as inductance. Before I start this topic, let me have some discussion, right? How this phenomenon called inductance can be. So let's talk about this. When we talk about solenoid, having current in a solenoid, and the current in a solenoid gives some magnetic fields, right? So the magnetic field produced by solenoid, one solenoid, is linked to solenoid itself. All right. So now I would like to connect the magnetic field, the current produced by a magnetic current. Alright, which produce a magnetic field, and that is linked to one solenoid or coil, right? So this connection is normally done by what phenomenon, what we call as inductance. Alright, so look at here, we talk about two cases, right? The first case is that I have a two solenoid, and having two solenoid, let's say I have two solenoid, and this solenoid, I have a current in this solenoid. Because of current in this solenoid, and the magnetic field or magnetic flux is given or is being given to next solenoid, solenoid 2, alright? And how it is done is given by what we call as inductance, alright? So this is what we have, right? This is what we call as a two solenoids are there. So we call it as a mutual inductance. Alright, so here the connection we are going to find out is the magnetic field given by a current in a one solenoid linked to other solenoid. This is what we call as a mutual inductance. And this is what we call as a self-inductance. Self means there is a current in a solenoid and which produces a magnetic field, and that magnetic field is linked or is given to a solenoid itself, and this is what we call as a self-inductance. Alright, so this is what we are going to do. Alright, and so now and then we talk about last time we talked about Friday law of inductions. If I change a current, there will be a change of magnetic field, and the changing magnetic field or changing magnetic flux give rise to current in another coil or a coil itself. So this is what we talk about, and therefore we say that since I discussed the two cases, right? One is mutual, one another one itself. So therefore current can be induced in a coil by a two-way, either by changing a current in a coil near or the particular coil itself, or changing magnetic flux or changing a current in a coil itself. So this is what we talk about. So I said an electric current can be induced in a coil by two ways, that is change produced by change, that means a current. We are talking about current, right? Change produced by change, that means current. Change produced by another coil in its vicinities, or a flux change produced by same coil. Or this is number one, this is number one, this is number two. Or else flux change produced by same coils. How do we change a flux? How do we change a flux? By changing electric currents. So changing current in a coil near one coil, or changing current in a coil itself give rise a current induced in a coil. So this is the case. All right, and then before I do this, all right, before I do that, what I'm going to do is we say magnetic flux. I say a magnetic flux. All right, magnetic flux linked to one coil is proportional to current. Is proportional to, if current is greater the magnetic flux is going to be greater. This is for one particular coils. Alright, so if I have an n number of coil, if I have an n number of a turn or coil, then this is what I have. So this current could be a current in another coil, or this current could be in coil 1 itself. This can be any, right? So this is proportional to I, and Ni is also proportional. This is one very important. This is where we are going to link. And now this, when I remove this, and then what we get is we get some constant, let's say K, and this constant K is what we call as this is constant proportionality. This constant proportionality. And this constant proportionality is what we call as inductance. This constant proportionality is what we call as inductance. Now, there can be a greater rate of change of flux if there is a greater rate of change of current. So this is again one case. So I just say that this is going to be again proportional to, alright. So there is greater rate of change of magnetic flux if there is a greater rate of change of current. So this is what and again constant is going to be inductance. This constant is what we call as inductance. Alright, so this constant I can rewrite. This constant can be of two cases. One is what we call as a mutual, right? N stands for mutual inductance. Mutual means there will be a two coil and one coil connect to another coil. And this K can be L if it's 1. This is called mutual inductance. This is called mutual inductance. Another one is called self-inductance. And the SI unit for inductance is what we call SI unit is what we call as Henry, right? SI unit is what we call as Henry, denoted by H. This is denoted by H. This is what we call as Henry, denoted by H. Alright, so this is what we have for inductance. This is what we have for inductance. Now what I'm going to do is, first I will do with mutual inductance, and then I will start self-inductance. So before I do this, this is the key, right? So this is going to be a very important formula, right? And this is going to be a very important formula, right? So now let me start what we call as a mutual inductance. All right, this is again mutual inductance. Again, this is image of mutual inductance. You see, there is a current, and this magnetic flux is linked to that coil, and that is what we call as mutual inductance. Flux is written, right? Alright, now I would like to start with mutual inductance. I said this, they can be of a different shape of mutual inductance. And before I start this, inductance which I discussed, either it is L or it is M, is defined by two factors, right? This is one is a geometry of inductance, another one is intrinsic property. Intrinsic property of material, right? Property of material. That's the point, right? So that we should keep in mind. We'll derive this also. Right? So now, as for our textbook, for our syllabus, we have this type of mutual inductance, that is coaxial solenoid. We call it as a coaxial solenoid. So I take a two solenoid, one is outer solenoid and the one is inner solenoid. So I take a two solenoid, two coaxial solenoid. Let's say two coaxial solenoids. I say inner solenoid. Let's say inner solenoid has radius R1 and then a number of turn per unit length. N1, this is N1 is what we call as number of turn per unit length, and N is a number of a turn. All right, N is number of turn, N is a length, and I say I is a current in a solenoid. So I1 is a current in a solenoid 1, I1 is a current in a solenoid 1, and now I have outer solenoid. Which has a radius R2, number of turn unit N2, number of turn N2, L is a length, same length, I2 is a current. Alright, so first let's talk about solenoid 1, right? So this is number of magnetic flux. This is the magnetic flux. I just say a flux linked to S1 due to current I2 in S2. Okay, so this is what I have is proportional to I2. This is proportional to I2, and then I remove this proportional sign. And I call it as M12. M12 is what we define as M12 is mutual inductance of S1 with respect to S2s. Mutual inductance of S1 with respect to S2s. And this is, let's say, equation number 1. Now I would like to write here what is N1, and this is N1 is number of turn, that is equal to N1L. And what is flux? Flux is going to be BA. B is due to solenoid 2, that is why I write B2. And this is, the area is A1, that is pi R1 square. Alright. Now look at here. And 1L, what is B2? We know solenoid. B is equal to mu naught and I. So therefore mu naught, N is 2, I is 2 pi R1 square. Alright. So therefore I will get 1 N2 then pi R1 square Li2. Alright. So now this is equation number 2. Now I compare equation 1 and equation 2. When I compare equation 1 and equation 2, what we get is M1 to I2 is equal to mu naught N1 N2 pi R1 square L I2 cancel out. This is what we call as mutual inductance. This is what we call as a mutual inductance. This is the mutual inductance of. Look at here. Look at the expressions, right? This is all geometry. This area is a geometry, length is a geometry, number of turn pi and length is a geometry, and this is a property of mediums. This is permeability, right? This is a permeability, which is what we call as property of medium, right? This is what we have. This is the mutual inductance of coil solenoid 1 with respect to solenoid 2. Now let's talk about M21. Let's talk about M21. So M21, what I'm going to do is I'll write here straight. This is the flux. This is the flux linked to S2 due to current I1 in solenoid 1. Alright. So, therefore, magnetic flux, this is a magnetic flux linked to outer coil, outer coil due to current in a inner coil. What is the current in the inner coil? I1. And therefore, I would like to change this. And this is M21 is mutual inductance of solenoid 2 with respect to solenoid 1. This is what we have. Now having this, now there is a little problem here, right? Now this is going to be M2, this is going to be 2. Alright, now this is going to be a number of turn, that is number of turn by the length, number of turn by the length multiplied by L is the number of turns, B2, and this is area. Look at here, this maybe you feel that this area has to be area of a second coil, but it is not so. The reason is that actually we feel that area should be area of a second coil, outer coil. However, it is not so. It is the area of only inner coil. The reason is that the magnetic field outside solenoid 2 is going to be 0. All right. Reason is that magnetic field due to I'll rub, then I'll write here, right? I'll write here. Area has to be area of inner coil. Inner coil. Reason is that no field outside S1. Alright, so therefore, what is the effective area which has magnetic field is going to be area number 1, right? Area has to be area of inner coil. The reason is that no field outside S1. So therefore, I take this. Alright. Now N2L1, and this has to be 1, right? This has to be 1. Why? This is magnetic field of solenoid 1. Alright, magnetic field of solenoid 1, right? And what is that? 1 mu naught N1 I1. Alright, and area is again 1 square. Now look at here. Again, I say this is going to be equation 1 and this is going to be equation 2. I'll rewrite this and make it little. Right. This is equation number 2. Compare 1 and 2. When I compare 1 and 2, what we get is M21 I1. This has to be 1. I'm sorry. This has to be 1. This is equal to mu naught N1 N2 by R1 square and I1. 1 cancel out. Finally, I got this is the mutual inductance of a second coil with respect to first coil. This is the mutual inductance of a second coil with respect to first coils. So the M12 and M2 are one and the same, right? So this is equal to Alright, provided L1 is equal to L2. Provided L1 is equal to L2. This is what we have in case of mutual inductance. And maybe what about this is the problem I would like to give you. What about if L1 is not equal to L2? This is the problem, right? What about if L1 is more than L2? What about if L2 is more than L1? So kindly solve this. Alright. What about if L1 is more than L2? What is the problem, right? If L1 is more than L2, what is the problem? Is there any problem? We just sort out, right? Alright, so this is it is easy to find out mutual inductance if L1 is greater than L2, or if it is easy to find out mutual inductance if L2 is more than L1. So I have done with L1 is equal to L2. Alright, so this is what we have for mutual inductance. Now, what I would like to do is, if I change the current in a, let's say, coil number 1, alright, so this is, if I change the current in a coil number 1, there will be a magnetic flux change in our coil number 2, right? This is the magnetic flux change in our coil number 2, right? This is the magnetic flux change in a coil number 2, right? So therefore this is equal to M21, right? di1 by di2, di1 by d2, right? So this is what EMF is equal to minus N2 d phi 2 by dt, which is equal to minus M21 di1 by dt. This is the answer, right? So EMF induced in a second coil, let's say I write here second coil. EMF induced in a second solenoid would be, this is what I have. This is how we would able to apply a law of inductions in a solenoid. So this is the basic principle behind the working of transformer. This we will do it later, right? This is what I have, right? This is for mutual inductance. Now I would like to do for self-inductance. Now I would like to do it for self-inductance. This is the problem I have given you. So let's do self-inductance. This is self-inductance. Alright, this is a self-inductance, and this again a self-inductance. Now for self-inductance, I will say flux linked to coil 1 itself. So I won't be writing 1 and 2. Alright, why? Because it is already 1. So this is what I have, and I would like to write L. This is for self-inductance. And then number of turn, less N is the number of turn per unit length. This is total number of turn. And then A is area of coils, and I is the current, right? So therefore this is equal to NL B A. What is going to be B? B is going to be mu naught and I A, right? So this is what I have. This is equation number 2, and this is going to become equation number 1. And I compare these two equations. When I compare these two equations, we get, and this is equal to N L mu naught and I A. I cancel out. L is equal to mu naught N square A L. This is what we call as self-inductance. This is what we call as self-inductance. This is what we call as self-inductance. that is magnetic flux linked to coil itself. This is what we call as self-inductance. Now what I would like to do is, what about if I change the current in a one coil itself, then there will be an induced current, right? So therefore I say this is going to be L di by dt. This is going to be di by dt, and then this is equal to minus N, and this is equal to minus L di by dt. So EMF induced is going to be minus L. And look at here, this L now act as inertia, and this L is the one that resists the change. Resist change means that coil experience a changing magnetic flux, and this L, what L does is L try to resist the change. All right. This is what we call as this act like inertia. This act like inertia. This is what we call inductance. Inductance is one that resists the change, right? One that resists the change. It is like inertia. Inertia is the one that resists the change of state of motion, right? So this is what I have. This is what we have. And then now what I would like to do here is, what about power, right? So we say that power is rate of doing work. Power is rate of doing work. So we say that this power is equal to I. Power is VI. This is a very simple formula. We have done it, right? So another word, power is equal to rate of doing work. Okay, and then now this try to figure out how it resists the change, right? And when it try to resist the change, there is opposite, restoring force or restoring work, right? So therefore this is going to be W by dt equal to which is equal to L di by dt I. Okay, and then now why? Because I substitute the value of this. Now this two cancel out, and dw is equal to Li di. Now I integrate this from 0 to I. Alright, so W is equal to integrating L I di from 0 to I. So finally I got W is equal to L I square by 2. So this is what we have. So this is the work done against the changing magnetic flux, and this is stored as a potential energy, right? So this is what we store as a potential energy. This is stored as a potential. This is stored as a potential energy inductor. This is a potential energy. This is a potential energy stored in a inductors. This is a potential energy stored in inductor, and this is very similar to kinetic energy, right? So this stands for, this is the rate of flow of charge, which we call as the velocity, and N is what we call as inductance, we call as inertia, that is M. So this is very similar to half mv square. V correspond to I, M correspond to L. So this is just for your reference, not for examination point of view, just for your reference. So therefore, what is the potential energy stored in an inductor? This is good. We have done a potential energy stored in capacitors, right? So this is a potential energy stored in an inductor. So that's the point. Alright, now what I would like to do here again, one more case is, so for mutual inductance, let's say this is number 2 due to this is equal to M2 to I2 plus M1 to 2 1 2 to 1. So this is what we have in case of, why? Because in case of mutual inductance, there will be two contributions, right? One from itself and another from, so this is what we call as self-inductance. This is equivalent to L, right? This is self. So therefore, then EMF would be equal to, and this is what we call the back EMF sometimes, right? Right, this is equal, right? So EMF induced is going to be minus L GI, this minus M21. This is for mutual inductance. Alright, so this is what we talk about self-inductance as well as mutual inductance. Okay. So now what I'm going to do is I'm going to do how do we get the continuous change of current, right? So we were talking about the rate of change of current, right? So for that, what we are going to do is what we call as alternating AC generators. So this is again important for next chapter also. So let me remind you that when we do the introduction to this chapter, we say that it was Faraday and Henry who discovered the electromagnetic inductions, right? Who says that the rate of change of magnetic flux will give rise current, right? Changing magnetic flux will give you a current, right? And it was and the electromagnetic induction is of a huge application in a day-to-day life, and one of the most significant applications of electromagnetic inductions was the construction of what we call as alternating AC generators. That means the AC generators, right? So electromagnetic, the foundations or the principle behind AC generator is electromagnetic inductions, laws of electromagnetic induction. And it was first designed by Nikola Tesla, all right? And so we say that when we discuss in our Henry experiments, Faraday and Henry experiments, we just bring a magnet here and there. Now, how he designed is he just rotate. When we rotate a coil, and there is a continuous change of magnetic flux, which gives rise current. So this is very, very important, right? So the AC generator was first designed by Nikola Tesla. Now this day we could able to generate 100 mega watt power, right, from using AC generator. So this maybe 90% of electrical energies were originated or is normally generated by AC generator. So it is very, very significant, right? So it means the results, right, of their finding, that is Faraday and Henry, was done by Nikola Tesla, right? So he could able to produce a lot of huge amount of power, right? So this is AC generators. This is a very simple diagram of AC generator. AC generator consists of armature or coil. This is a coil. I have an axis, and you are going to rotate about axis. So what you are going to, the mechanical energy rotates the armature or coils, and you will be having a two slip rings, and this is the brush. Brush are the one that connects to an external circuit. All right, and I have a two magnets. And this is how you. And how are you going to rotate? Coil means by different means. That is, if I let a water to fall, and this is what we call the hydropower, right? I just allow a water to fall on a blade or sharps, and then this rotates, and consequently this is going to rotate, and we could able to produce a power, right? And in case of steam engines, steam rotates this, right? So this is our textbook diagram, right? Textbook diagram for AC generators. I say these two are the slip rings. This is the brush, carbon brush, and this is alternating current, this is axis, this is coil, and what we have, two generator, right? So this is what the principle is electromagnetic. So I just write here. Principle is Friday law of inductions. Alright. So what I'm going to do is now I say a flux. What is flux? Flux is equal to BA. Alright, flux is equal to BA. Alright. And I have a number of turns. For n number of turns, this is going to be NBA. I'm sorry, this is cos omega cos theta and cos omega t. Now since I'm rotating, omega is angular frequencies, right? Angular frequency. Omega is angular frequency, and B is a magnetic field produced by this. A is area, and N is the number of turns, right? So this is what this is the flux, magnetic flux. Now what I'm going to do is, what is EMF produced? EMF produced will minus. This is EMF produced, and therefore this is going to be NBA cos omega t. I differentiate this. When I differentiate this, this is equal to NBA minus sine omega t divided by omega. I'm sorry. Right. Omega minus sine omega t. I'll write it like this. Maybe since we have finished differentiation, right? So first I'm going to differentiate this. And minus sine omega t, then I'm going to differentiate this omega, and minus into minus is plus. This is equal to BA omega sine omega t, and minus into minus is plus. This is EMF produced, and this is EMF produced, and this is what I call as sine omega t. This is the amplitude of EMF. This is amplitude of EMF, and then I'm talking about this. Omega is angular frequency, and then E is instantaneous EMF, that is EMF at given time t. So this is what we have. So this is the most important formula here, right? So this is what we call as alternating. This is what we call as alternating EMF or alternating voltage. So this white box, you will see. The sine is a sinusoidal, right? Sine is a sinusoidal functions. So that means EMF, right? How EMF generated means this is how EMF is given by sine function, right? EMF is given by sine function, right? So for theta is 0, EMF is equal to 0. Theta is equal to 90 degree, EMF is equal to maximums. Theta is equal to pi, EMF is equal to 0. This is how it goes, right? Alright, this is how it goes, right? Alright, so this is what I have, right? So this is what I have in case of this, right? So this is how flux changes, alright? And this is how EMF changes. I'll give you. This is there in your textbook, alright? This is there in your textbooks. If theta is equal to induced EMF, right? So this is how it goes, right? EMF is 0 for theta is 0, and this is EMF is maximum when theta is 90 degree, EMF is 0 when theta is pi by 2 pi, and this is how it goes, right? This goes along with time. And one more I would like to convey you is time period. I would like to give a relation between a time period and a phase. This is one time period. This one time period corresponding to 2 pi phase, right? 2 pi phase. So therefore, half time period is corresponding to pi, and this corresponding to pi by 2. So this is what we should keep in mind. So this is what I have. This is how. So what is alternating, right? So what is alternating means the voltage. What is alternating means this is the voltage, right? So first time this is going to be a positive. After half a time period, this become a negative. This become positive. And next half a time period, this become a positive. This become negative. This is how it goes. So this goes with the sign, right? This goes with the sign functions. This goes with the sign function, right? So this is what we have. All right. This is what we have, right? This is right. This is, I can say this is time, and then this is EMF, EMF naught minus EMF naught. This is going to become T by 2 half time periods. This is quarter time period. This is 3 by 4 time periods, and this is going to be time 1 time period. This is pi by 2 pi, then 3 by 2 pi, and this is 2 pi. So this is how it goes. So therefore this is what we call as alternating. Alternate means changing. What changed, right? Polarity is changing, right? Polarity is changing, or one case it is alternate. So this is alternate. And another term is what we call as a sinusoidal, right? So this is order. This is what we talk about alternating current or alternating voltage. That means this is equal to, this is 0 for omega t is equal to 0. This is equal to plus omega t is equal to pi by 2. This is equal to 0. Omega t is equal to pi. This is equal to minus pi naught. Omega t is equal to 3 by 2 pi. And this is equal to 0. Omega t is equal to 2 pi. So this is what we have. So with this we come to an end of chapter number 7, I guess. Thank you.